So I'm Professor Julie Lundquist in the Department of Atmospheric and Oceanic Sciences, and we're very, very pleased today to have Mark Jacobson here. Mark is telling me over breakfast that his role in life is to understand problems and then figure out what to do about them to solve them. And I think that that's a great way of motivating anyone's life. The main goal of his research is to understand better the severe atmospheric problems that we are encountering, such as air pollution and global warming, and then to develop and analyze large-scale clean energy solutions to those problems. And so Mark has done considerable work in developing numerical models that we use to explore problems, identify possible solutions, and then test out those solutions. He's also made some great contributions in the area of education. So he's published 2 textbooks that have gone into multiple editions each, and he has over 135 peer-reviewed articles. So in recognition of his substantial contributions, he's received awards from the American Geophysical Union and the American Meteorological Society. And these, in atmospheric sciences, these are called kind of the superhero awards that Mark has received, which is pretty amazing to receive multiple of them so early in a career. And the Global Green Policy Design Group has also awarded him an award for the design of analysis and policy frameworks to envision a future powered by renewable energy. So, the introduction could probably go on for the entire hour, so I'll stop talking here and turn it over to Mark. Let's give him a round of applause.
Thank you very much, Julie, for that kind introduction. And I'm glad to be here to talk about these plans that we've been developing for changing the infrastructure of states and countries to clean and renewable infrastructure. So I'm going to talk about these state plans in particular, but I want to motivate it first. What's the problem? Why do we need to act quickly? Because there is plenty of energy around, conventional energy around to go on for quite a while. But from our point of view, it's because of air pollution and global warming and energy security, including energy price security. 2.5 to 4 million people die each year prematurely from air pollution worldwide, including 50 to 100,000 in the United States. And this is from cardiovascular disease, respiratory illness, complications from asthma arising from pollution particles and some gases as well. And climate change is a severe and growing problem. The Arctic sea ice may disappear within 10 to 30 years, and that will cause additional positive feedbacks to warm the climate system more. The temperatures are rising faster worldwide than at any time since deglaciation from the last ice age. And there are a lot of problems associated with climate that I don't have time to go into, but it's a severe and increasing problem. We'll discuss a little bit more. Population is growing as well, and energy demand is growing, especially in developing countries that are now realizing their potential for using energy. And this is going to result in energy price insecurity due to the fact that fossil fuels have to be continuously mined and transported and used, and so their prices gradually go up over time, especially as they become shorter and shorter in supply. And so eventually, this could cause some chaos in societies because the prices of fuels become so high. And so what we need is some type of energy technologies that really do not grow in the price because their fuel cost is zero. And so this is one motivation for looking at clean renewable energy sources. So these are all drastic problems, and they require drastic solutions. Now, just to give some indication of pollution around the world, I mean, it looks in Colorado, it's beautiful. There's not so much pollution, although Denver always used to have or still has to some degree, brown cloud. Los Angeles has always been polluted, the most polluted city in the United States. And there are many, in fact, 6 of the 10 most polluted cities in the United States are in California. And still, as I mentioned, 50 to 100,000 people die per year in the United States. But around the world, a lot of the world looks like this. This is Beijing in 2013. It looked very similar in 2014. And it's like smoking 2 packs of cigarettes a day here. In another city in China, in Linfen, it's like smoking 3 packs of cigarettes a day. This is Sukinda, India. A lot of chemical factory burning and power plant and other types of industrial exhaust on top of vehicles and motorcycles and indoor burning of biofuels and biomass. This was Los Angeles in 2000 and has a smog layer that is unparalleled in the United States and is traditionally the home of most air pollution. And it was like in the 70s smoking 2 packs of cigarettes a day there. And these, in fact, these are the lungs of a teenage non-smoker who died in a car crash in the 1970s. And you can see exactly what air pollution does to your lungs. And it's a problem that is severe and continuing to occur. So we're looking at solutions not only to global warming, so reducing carbon, but also all air pollution. So this would involve trying to eliminate combustion as much as possible. And of course, the growing climate problem increases sea levels slightly so far, and this results in more intense impacts of hurricanes, such as this Hurricane Sandy causes more flooding because sea levels are already slightly higher due to the thermal expansion of water, and because you have more intense hurricanes, and this causes greater storm surge and more flooding and more coastal damage, and this will increase over time unless we do something about it. So we've looked, in 2009 we did a study looking at, well, what are some possible options for addressing global warming, air pollution, and energy security. And we looked at the externality impacts of different energy technologies, about 12 different externality impacts, including their effects on climate, air pollution, land use, water supply, catastrophic risk, on wildlife, on reliability. And we came up with a recommended list of options, and options that were not so recommended, not necessarily because they're not better than what we have today, but because they are not so good as the recommended options. And we did it for electric power and for vehicles at the time. And the recommended electric power options were what we call wind, water, and solar options, or WWS. And so they included wind and concentrated solar power, CSP, geothermal power, solar photovoltaics, tidal and wave power, and hydroelectricity to some extent, although we probably wouldn't grow hydroelectricity very much, if at all. And then for transportation, the best options were these electric power options powering battery electric vehicles, or to some extent hydrogen fuel cell vehicles. And then we can extend this to other sectors of the energy economy, including heating and cooling, using electricity for air source and ground source heat pumps, and some resistance heating, and also in industry using electric resistance for high temperature processes or hydrogen for high temperature processes. But what was not recommended were nuclear power for electricity or coal or carbon capture and sequestration, natural gas or biomass for electricity, or for transportation, liquid fuels such as corn and cellulosic and sugarcane ethanol, soy or algae biodiesel, or compressed natural gas. So you might ask, well, why? And so I'll just give you briefly some reasons why you would not use these other options. Well, why not natural gas? Again, we're looking at, since we have to solve these problems rapidly, we can't put in new natural gas facilities because they'll be around 30 or 40 years and they'll still put out a lot of not only carbon but air pollutants. And for example, it's 50 to 70 times more CO2 equivalent emissions per kilowatt hour generated for natural gas than for wind power in the if you look at the life cycle. Then the methane from natural gas leakage contributes to Arctic sea ice loss, and that's over a short time period, and we're really concerned about the Arctic disappearing really rapidly. And also black carbon from from natural gas flaring also contributes to Arctic sea ice loss. The air pollution from the mining, the transport, and the use of natural gas causes 5,000 deaths per year prematurely in the United States. It's less than coal, but it's still much, much greater than wind or solar. So when you're siting a natural gas facility, the gas operator will say, well, we're not actually emitting a whole lot from the natural gas. It's, we've got these control technologies, and there's not a lot of emissions. Well, there are more control technologies, but there's still a lot of emissions of oxides of nitrogen, ammonia. there's not much sulfur from natural gas, but you get some carbon monoxide, in addition to the carbon dioxide. But they're pollutants that do still lead to air pollution. But it's not only the emissions from the actual plant, it's from the upstream production of the fuel that you get a lot of the emissions. So whenever you put in a natural gas plant, you don't only want to consider what's the local emissions from the plant, you want to consider the entire upstream production of fuel and transport, the mining, and the conversion of the fuel if necessary. So there's a lot, that's why you get these 5,000 deaths. It's not just from the emissions from the plant itself. And then hydrofracking is a method of extracting natural gas, which you crack rock with water under high pressure and laced with chemicals. And this not only causes risk to groundwater, but also increases the methane emissions. Okay, so these are reasons why you wouldn't want natural gas versus renewable energy sources.
Sorry for interrupting you. I heard from someone in the back that your microphone isn't working, so do you want to try and use this one instead?
Sure. Sorry for that. Is this better? Okay. So why not what's called clean coal, or coal with carbon capture and sequestration? Well, this is where you remove CO2 from the exhaust of the stack, and it removes about 80 to 85% and then sends it underground where it's kept in a reservoir, where there could be some leakage. But that's not the main issue. The main issue is you don't reduce any of the mining or transport emissions associated with coal. In fact, you need 25% more coal to run the carbon capture equipment, so you have 25% more mining and transport. And you don't also reduce any of the other emissions associated with coal burning. And so in fact, you have 25% more pollution associated with the rest of the coal. That includes like mercury and hydrocarbons, oxides of nitrogen, sulfur oxides, particulate matter. So it's really should be called dirty coal because it's actually dirtier. The only thing that's being reduced is carbon dioxide. But even the carbon dioxide still results, the reduction still results in 50 times more CO2 per kilowatt hour than wind. Why not nuclear power? Well, people say, oh, it's carbon free. Well, it's not. You actually have 9 to 25 times more carbon equivalent emissions and air pollution from nuclear than you do from wind power. And half of that's due to the continuous mining, refining, and transport, although that's minor, of the uranium that you would need during the life of the nuclear power plant. And the other half is the fact that it takes so long to permit and then construct a nuclear power plant, with 10 to 19 years on average in the US, compared to 2 to 5 years for a wind farm or solar farm, that in the meantime you're running the electric power grid that's consisting primarily of coal and gas. So it's an opportunity cost emissions due to the time lag between planning and operation of the nuclear plant and compared with some other facility. Well, in addition to the emissions, you also have the risk of meltdown. 1.5% of all nuclear reactors ever built, there have been about 440 built, have melted down to some degree. And 5 countries in the world have secretly developed nuclear weapons capabilities under the guise of civilian nuclear energy programs. So if we wanted to power the world on nuclear, we'd need about 16,000 large nuclear power plants, about 850 megawatts in size. And we only have 440 today, so if you doubled the number of nuclear reactors, that's about on the order of 800 or so, and that's about 5% of the energy. And so many more countries of the world would suddenly have nuclear reactors and would be able to consider developing weapons secretly under the guise of these nuclear energy facilities. So that's a risk that you don't have with wind or solar or geothermal or some of these other clean energy technologies. And there are also unresolved waste issues. Well, what about biofuels? Well, why are they an issue? Well, in terms of air pollution, ethanol, regardless of whether it comes from corn or cellulosic material or sugarcane, it's still ethanol, and when it's burned, it produces lots of aldehydes. And the aldehydes, when you look over the entire United States, based on computer modeling simulations of the impacts of an ethanol-fueled fleet versus a gasoline fleet, one of the studies that we did found that in Los Angeles, you would increase the air pollution mortality rate due to the enhanced ozone from ethanol by about 9%, and in the US as a whole, it's about 4% You get some reductions in the southeast of the U.S., but along the coasts, along the west coast and the east coast, you get increases, and most of the inland you get increases. So there's no benefit from an air pollution point of view of using ethanol or any other biofuel because they're still combusted and burned, and you produce aldehydes or instead of aromatics, and the aldehydes are more potent in terms of producing ozone. But in terms of land use, cellulosic ethanol to power the U.S. vehicle fleet would require between 5 and 35% of the entire U.S., including Alaska, to grow the switchgrass. And this represents an average, this blue dot. The 5% was the industry estimate, and the 35% was from the scientific studies. But anyway, so this is just a compromise in between. For corn ethanol, and by the way, cellulosic ethanol, it's been proposed since 1981, but there's still not a single commercialized cellulosic ethanol factory anywhere in the United States. Corn ethanol, 10 to 18% of the U.S., so on average about 14% to power the U.S. Vehicle fleet. For nuclear, that's not its big issue, the space. It wouldn't take up so much space. It would take up about the size of Rhode Island to power the vehicle fleet. So we can sacrifice one state there. But for wind, it would require, there's two types of areas. There's the footprint area, which is the land on the ground for the wind turbines, and there's the spacing area between turbines. To power the U.S. vehicle fleet, you need about 73,000 to 144,000 5-megawatt wind turbines in wind speeds of 7 to 8.5 meters per second at hub height. And so that would take less than 3 square kilometers of land on the ground touching the topsoil of the ground due to the poles and the little concrete around the poles that are above the surface. And so that's the least land invasive technology to power any energy infrastructure. The spacing between turbines is about 0.5% of the U.S. land area, or about one-third of North Dakota. But that land can be used for multiple purposes, including rangeland and farmland and agricultural land or open space. And a lot of it can go offshore. The East Coast offshore is the largest wind resource, unexploited wind resource in the world. Of course, the Great Plains has the greatest potential in the U.S. But solar and geothermal, solar takes about 1/3 the land area to power the vehicle fleet as the spacing area for wind, but a larger footprint. Geothermal is even less spacing area than wind or solar. So you could, with geothermal, wind, and solar, the areas are not large, and it'll turn out the impacts are small as well in terms of trying to reduce air pollution and climate emissions. So let's look at some numbers for, well, can we power the entire world or the U.S. or individual states with wind, water, and solar power? And so worldwide, in 2010, the world end-use power demand was on the order of 12.8 trillion watts. If you go to 2050 with current fuels, it'll go up to 21.5 terawatts. And if you actually then convert everything for all sectors, that's including electricity, transportation, heating and cooling, and industry, to wind, water, and solar electricity, and so even the hydrogen's produced from electricity, then you reduce your power demand by about 30%, going down to 15 terawatts of demand, and this is 2050, because of the efficiency of electricity versus combustion. And a lot of this improvement is in transportation. So for example, an electric car has a plug-to-wheel efficiency of 80 to 86%, meaning 80 to 86% of the electricity going in the car goes to move the car. The rest is waste heat. An internal combustion, gasoline or diesel or ethanol vehicle, traditional fuel tank-to-wheel efficiencies are like 17 to 20% or so. So that means only 17 to 20% of the energy goes to move the car. The rest is waste heat. And so you actually need less energy to drive an electric car. And that's why the cost of driving an electric car is equivalent to 80 cents a gallon versus $4 for gasoline. So this reduction in energy demand due to converting to electricity results in, without even having to change your habits, you can just reduce the demand. So these demand reductions are only 5 percentage points of these demand reductions shown are due to end-use efficiency measures, although you could probably get a lot more end-use efficiency measures. So most of this is due to just the efficiency of electricity versus combustion. In the US, you'd get a 37% reduction in energy demand because there's a lot more transportation than on the world average. In California, there's even more transportation than in the world average, than in the US average. So you get even higher reduction in demand just by changing to electricity without changing habits. In Colorado, it's about 37% benefit of demand reduction of energy. And only, again, about 5 percentage points of this is due to end-use energy efficiency improvements. So the goal, let's say in Colorado, would be for 2050, would be to, how do you power 0.032 terawatts of power demand at that time, which is less than even today, or in 2010, which is 0.037. Well, so let's look at the world. So this is one way you can do it. This is, again, for all purposes. For the world, you could do it with 50% wind, 40% solar, and 10% everything else. So that means about 4 million large wind turbines, 5 megawatts. And that 4 million turbines, well, it sounds like a lot, but it's one-time production of these turbines, effectively. And in World War II, the world produced about 800,000 aircraft in 5 years. So we're talking about producing 4 million turbines between now and 2050, with most of them by 2030, hopefully. So there's plenty of time to actually get this rolling. This is worldwide. Now, in terms of solar, it's 40% solar. It's broken up into rooftop solar PV plants, and CSP plants. And then geothermal and hydro about 4% each, and tidal and wave are a small 1% each. And this is so we developed plans now for all 50 states, at least the numbers for them, and a lot of statistics, and I'll show you a website where you can get these numbers later. But these are some numbers for Colorado. This is just one way to power Colorado for all purposes, to eliminate its global warming emissions, to eliminate all air pollution emissions, and to provide energy price stability. So this would be with 60% wind and 31% solar, and about 5% geothermal and 4% hydro. So again, this is not necessarily what we're prescribing. This is just one possibility. So there's a lot of shifting that's possible. But that's about 12,000 5-megawatt wind turbines, 1.7 million 5-kilowatt residential rooftop systems, 78,000 100-kilowatt government commercial rooftop systems, 420 50-megawatt solar PV power plants, about 185 100-megawatt CSP plants, and then about 18 geothermal plants and 1.4 hydroelectric plants. Now, if we go to California, which has a higher demand overall, and coastline, so you can start using offshore devices, then it'd be 25% onshore wind, 10% offshore wind, then break up the solar into 10% residential rooftops, 15% commercial government rooftops, 15% solar PV plants, 15% CSP plants. Yeah. Concentrated solar power, where you focus light off of mirrors onto a central tower receiver to heat a fluid such as a molten nitrate salt, which can then be either used immediately to run a steam turbine or to store it overnight to generate solar electricity at night. That's the advantage of CSP, is you can use it for storage and to firm the grid by producing nighttime electricity. And just a tiny amount of tidal wave. For the hydro, it's all existing, so we wouldn't even increase any hydro in California. Just to give you a land area, this is how much land and water area would be required for this California plan. The green is the onshore wind spacing. Can be used for multiple purposes, such as farming, agricultural land, rangeland, etc. The red is solar and CSP power plant areas. The yellow is rooftop solar. The blue is offshore wind. And those red dots in the middle of the green and the blue are the actual footprint on the ground of the wind, either onshore or offshore wind. And there's a small amount of geothermal, and we're not adding any new hydro, so there's no additional hydro land area required. It's all existing. So this is additional areas beyond what's existing in California that would be needed. But again, also this does not account for the fact that you're removing the fossil fuel, the nuclear and the biomass industry infrastructure as well, all the pipelines and power plants, as well as refineries and gas stations, et cetera. And for New York, here's another plan with the areas required. There's more offshore wind potential in New York. And so that's the blue offshore, and then there's blue onshore wind. And red is CSP plus PV power plants, mostly PV. And that's the dark red. The light red is the rooftop PV. Now, this would take, both in California and in New York, it's on the order of 1% new land area and about 2 to 2.5% spacing area that's needed. But to put in perspective, agriculture in New York is about 20 to 25% of the land areas for agricultural purposes, and 3% of New York is covered with housing or buildings just on agricultural land. Now, here's another area thing for Washington State. Washington State's a little easier because it has so much hydro already in place. And so it would need some onshore wind, which is the green, and offshore wind, which is the blue, and some solar, mostly PV, and a tiny amount of geothermal. This is, again, to power the states for all purposes. Just to give an idea of what are the resources available. And so for solar, this is a standard solar resource map of the US. And even though the solar is not so good in the Northeast, it's actually not real bad. In New York State, it's about 4 to 4.5 kilowatt hours per meter squared per day, compared to on the order of 6 kilowatt hours per meter squared per day in the Southwest, which is the best resource. But so you're going to take an efficiency hit, so that'll increase the cost slightly, but it's not a huge amount. And so you can have solar in all states of the US. And Germany has higher latitude than most of the US and has covered the entire country with solar. And even though it's less efficient than at lower latitudes, it does not only generate electricity, but it spurs jobs in industry, which is an important part of any of this. The building of these devices and plants actually then improves the economy as well. So I'll discuss that in a little bit. So in terms of wind resources, this is a map of the world wind resources from computer modeling at 100-meter height. And the relevant, in 2030, the power demand needed for the world is about 11.5 terawatts. By 2050, it goes up to about 15 terawatts. But for 2030, then you would need about 11.5 terawatts, and there's about 70 to 80 terawatts of wind power at all wind speeds over land and over land worldwide outside Antarctica. So it's about 6 to 7 times more wind alone than you could need to power the entire world for all purposes. But we'd really only want to power half the world, so it's about 5.75 terawatts at that time. Or if you go to 2050, it's about 7.5 terawatts that we need. So there's plenty of wind to power the world. There's actually more solar than wind. There's 330 terawatts worldwide in high solar locations. Now you can see off from this map that in the US, the Great Plains and also Colorado has huge wind resources. But offshore the East Coast, there's a lot of wind resources in shallow water. The West Coast also has strong winds, but the water is much deeper. But the East Coast and also the Gulf Coast, there are a lot of hurricanes come by. And so you might ask, well, what's the impact of the hurricanes on the wind turbines? And then on the other hand, if you put a lot of offshore wind, then on the other hand, you might ask the other question, well, what would the wind turbines do to the hurricanes? So it turns out, so this became an interesting issue. Well, so wind turbines are designed to withstand winds up to 50 meters per second, which is between a Category 2 and Category 3 hurricane. Now, it turns out off the east coast of the U.S., the winds never get up to much more than a Category 2 hurricane. Usually they're Category 1 or even less. So you rarely have Category 3 or never 4s or 5s. You do get some Category 3s. So if you have isolated turbines along the east coast, it's be a low chance that a hurricane would destroy the turbines. Now on the Gulf Coast, it's a different story. There's a higher chance because you do get several Category 4 and 5 hurricanes going through the Gulf Coast. But you could strengthen the turbines as well. There's no reason they can't be strengthened. But also it turns out, so we were interested in this and ran simulations of, well, what if we had a lot of turbines? Could they actually reduce the wind speeds in the hurricane sufficiently such that you don't actually get wind speeds that would destroy the turbines? And so this was simulations of Hurricane Katrina, from Hurricane Katrina. The left is a simulation before the hurricane hit land. Or this is an image before the hurricane hit land with no turbines present. And this is wind speed at near the surface. And the reds and whites are higher wind speeds. And on the right is a simulation doing the same thing, except you had a bunch of turbines, actually about 70,000 turbines just to the southeast of New Orleans. And it's kind of in that triangle area where you have blue, where you've cut out you reduce the wind speed significantly. So it turns out that, well, not only do you reduce the wind speeds locally behind the turbines, because the turbines extract energy from the hurricane, but that reduction in wind speed also reduces the wave heights, which feeds back to reduce the convergence of air to the center of the low pressure system, and that results in higher pressure in the center, so that over time the central pressure actually increases in the hurricane. That weakens the overall hurricane. So it turns out you never actually get wind speeds that reach, because the turbines first see the outer rotational winds, which are slower, and then that results in a feedback to weaken the entire hurricane. And so then the wind speeds never actually reach the destruction speed, even in Hurricane Katrina here, if you have enough of them. Now, if you don't have enough, then the other thing happens. But so here's a few hours later, when the hurricane's hitting land, you can see that where that blue is in the center, you pretty much killed off a lot of the hurricane. And so we found that you can actually reduce the storm surge by up to 80%, because the storm surge is based on the wind speeds over a long fetch and over time. And so you can reduce the storm surge, and it's proportional to the average wind speed squared. You reduce the wind speeds downwind of the turbines by about 50%, and the storm surge by up to 80%. So those are the two things that cause destruction, are the storm surge and the winds. And so we also did for Hurricane Sandy and found similar results, and also Hurricane Isaac. And so this is a study that's coming out next week. But the thing is that then you might ask, well, what's the cost of this? Well, these turbines would be put up offshore, not necessarily for stopping hurricanes, but just for generating electricity normally. So they pay for themselves. They're designed to pay for themselves just from normal electricity generation during the year. And the transmission is sized such that the transmission will transmit all the electricity that they produce. Just so happens that if a hurricane comes by, they can also reduce impacts of the hurricane. So that's an additional benefit. But the cost is just the normal cost of offshore wind, which is more expensive today. But if you did this on a large scale, it would be on the average of around 10, 11 cents a kilowatt hour. And that compares to now that's just the actual generation cost. I mean, there are also additional costs through utilities that charge. The average price of electricity in the US is 13 cents a kilowatt hour. In New York, it's 18.1 cents. And in Hawaii, it's 33 cents. So this puts it in perspective. But onshore winds in the Great Plains can be down to 2.5 to 5 cents a kilowatt hour, just the actual raw cost of the turbines and local transmission. And so offshore wind is more expensive. It's like doubling the price of onshore wind right now. But it has this additional benefit. So the alternative is putting up seawalls. Now seawalls or storm barriers, they serve one purpose, which is reduce storm surge, but they don't actually reduce the wind speed of the hurricane. And they would cost a huge amount, like $30 billion just to protect one city. So they don't generate electricity. So they don't pay for themselves, except to the extent that they can reduce the storm surge. So anyway, this is just a possible additional benefit of offshore wind. Okay, well then what about reliability? People ask, well, if you put up wind doesn't always blow, the sun doesn't always shine. Well, that's true, but by combining wind and solar, it turns out that they're very complementary in nature. So when the wind's not blowing during the day, often the sun is shining, and vice versa. So this is results from a study for California from 2005 and 6, looking at could we power the demand over 2 years, every hour over 2 years in California from just wind and solar and geothermal and hydroelectric, which would be used to fill in the gaps. So this shows 2 particular days, and the black line is the power demand on those days. The red is the geothermal, which is base load. The light blue is wind, which often peaks at night in California over land. The yellow is PV, and the orange is concentrated solar power with some storage. So that's why there's a little bit of orange at night, because you can generate some electricity at night. And the dark blue is hydroelectric, which is used to fill in the gaps. But again, we did not increase the hydro, we just used the same amount that's existing. Then the gray is backup, which was natural gas, which wasn't used on these 2 days. And so in fact, it was found that natural gas was only needed on 0.2% of all the hours over 2 years. So in other words, 99.8% of the time, you can have a reliable grid with just wind, solar, geothermal, and hydroelectric. And this was without any battery storage. It excluded demand response management, which would shift the times of peak demand. It didn't treat electric vehicles, which are also flexible loads that could then be used to shift the time of peak demand. It didn't consider oversizing the grid, which is another way, because we're trying to power all sectors of the energy economy. So if we have more wind and solar than we need, it makes it easier to match the power demand hour by hour. And then when we have extra wind and solar, we use it to generate heat for city heating or for hydrogen production. And in Denmark, all the extra wind is used for city heating. Right now in the US, when you have too much wind, you just curtail it and you waste it. So this would be a more efficient system, actually using that extra energy for other purposes. Now, what about the costs? So this is where the key is. Today, the bottom line here shows the cost of conventional electricity. That's mostly coal and gas. It's 9.2 cents a kilowatt hour, the levelized cost of energy, with another 5.5 cents a kilowatt hour for health and climate costs. So it's a total of 14.5 cents a kilowatt hour. If you go forward, just extrapolating the last 10 years to the next 10 to 20 years, you get up to 14 to 19 cents a kilowatt hour for the levelized cost of fossil energy. And plus the externalities gives you 20 to 25 cents a kilowatt hour. Now, onshore wind and geothermal and hydroelectric are very cost competitive today. And this is why you've had so much onshore wind growth in the US. But the others are more expensive in terms of their direct cost. But by 2020 to 30, because you have zero fuel costs and their technologies are improving, all the costs of the other ones are going to go down or stabilize. So it's ultimately all the wind, water, and solar technologies will be less expensive than fossil fuels, just because you have to keep mining and transporting fossil fuels. And you can see this already in some of the data. If you look at the 10 states in the US with the highest percent of their electric power from wind, and the top 2 were Iowa and South Dakota last year, with 28% of all their electricity from wind, and Texas was number 10. their cost of electricity in those states went up 3 cents a kilowatt hour from 2003 to 13. All the other states went up 4 cents, and Hawaii went up 17 cents a kilowatt hour. It's because you have this rising gradual price of fossil fuels. And you might say, well, natural gas is now low, but if that's just in the last year or two. So if you look over a 10-year period, fossil fuels have gone up, and they're expected to still go up, even though you'll have temporary drops. And this will result over time in stabilizing. If you use wind, water, solar, you'll stabilize the prices of electricity. Well, what about the additional health cost savings? If you convert to wind, water, solar, and this is a summation over all the 50 states, well, air pollution, as I mentioned, kills on the order of 60,000 people per year, and there's a range of high and low numbers. But this cost, if it's 60,000 people, is on $530 billion cost to the US, which is about 3.3% of the GDP. So you can go through every state and you'll find numbers on the order of 3% or more, up to 7% for California. And so you do get the savings, but you also generate jobs. If you look state by state, we generate 5.1 million 40-year construction jobs and another 2.6 million 40-year operation jobs from this conversion. Now you'll get job losses as well, but overall in the US, there'll be a net gain. In most states, there'll be a gain. Some states, there'll be a loss. For example, in California, the gain minus loss would be about 200,000. But certainly, maybe West Virginia, you might have a net job loss. So there are going to be shifts, but because, especially in the solar industry, per kilowatt hour, solar jobs are much greater than gas or coal jobs. And so and you can see this. There was one study that found that in the last year, there was more jobs in the solar industries than the gas and coal industries combined in the United States. I mean, 34% of all the new electricity in California last year was solar, for example. And so there's a huge, for construction purposes, there's a lot of job creation. So here's kind of a pathway towards 100% renewable. This is for the Washington State example, where they have a lot of hydro already. So we're just keeping the hydro as a constant level of energy. But if you look at the projected demand, if you don't do anything, you follow the top line, the projected demand in energy. But if you convert to wind, water, solar, you get a reduction in power demand just due to the efficiency of electricity, and then you get additional end-use efficiency reductions of demand. And then that 100% line in 2050, that's what you have to power by wind, water, and solar. And again, this is for all purposes. And in this case, it would be for Washington is 43% wind, 28% solar, 26% hydroelectric, and 2% geothermal. And the hydro is really valuable in being able to load balance to fill in the gaps when there's no wind or solar. And so we did this for all 50 states, and here's some, you can't really read these, so I don't want to pretend as if you can, but just gives you an idea of some of the calculations that were done. So these are 40-year job production calculations for different states, such as California, Pennsylvania, Georgia, Illinois, and Ohio. And air pollution mortalities, we find a lot more mortalities in California than in other states because it has 6 of the 10 most polluted cities. And even though it has some of the best regulations, there's just still a lot of pollution. And we have the Pacific High that traps pollution in the Los Angeles basin, and you get a lot of the pollution in the Central Valley as well. But avoided air pollution mortality and morbidity cost as a percent of state GDP. If you go to wind, water, solar, and these are the top states, so up to 7% for California, but surprisingly even Kansas has a lot of pollution per capita. And so these are things that people usually don't think about. They health costs that are associated with energy when you're looking at trying to put a cost on energy or to compare clean energy sources. This is something that's pretty obvious that should be accounted for. So to summarize, and these are some statistics for the entire US, that converting to wind, water, solar, plus electricity and hydrogen would reduce U.S. power demand by 37% on average, eliminate about 59,000 air pollution deaths, about $530 billion per year, 3.3% of the GDP of the U.S., eliminate another $730 billion per year in global climate costs by 2050, just not mentioned, create about 7.5 million jobs for 40 years. The energy cost savings. So if you actually extrapolate the future cost of energy to 2050 from conventional fuels, you saw that was going up over time. And you just extrapolate it forward, and then you extrapolate, if you use the constant cost of renewable energy sources, you end up, and then you look at per person per year in the US, the average person, because the cost of electricity from fossils is going to go up so high by 2050, just through a straight extrapolation forward, compared to stabilizing the prices from wind, water, solar, each person would save $3,400 a year by then. And the health and climate costs are another $3,100 per year. The footprint area of the states to implement this plan is about 0.65%, and the spacing area is about 2%. And there are many methods of addressing the variability. Materials are not limits, but recycling would be needed at some point for some of the devices. There are barriers in terms of upfront costs, transmission needs, of course, lobbying and politics, although these are not technical or economic barriers. They're more zoning and political barriers. And just if you want more information on this, here's a website that has kind of all our state plans so far, and also the 50 state statistics, and also an infographic that I'll show you an example of in a second. And there's a group that we've been working with to take these plans and try to implement them on a large scale called the Solutions Project. And on the bottom left are a bunch of students, along with Mark Ruffalo, who's in the center there, who've been helping out to develop these plans. We've had, each of the last 3 years, we've had a lot of students. This year we had 30 students. Last year was about 25, and the year before was about 14, 15, who are just volunteering their time to help out developing these plans and making them better. And the Solutions Project involves not only science, but also business people and policy people and artists and entertainers. And we had last week at Daytona, there was a race car driver who had a Go 100% renewable sleeve on her car. And she was really interested in helping promote this energy plan. But it's interesting because there's another car, because her car has a sleeve that says Go 100% renewable, and there's another car that has a sleeve that says Clean Coal. so it's kind of funny, but anyway, so it's just another way to get information out, because part of this is energy education to the public and policymakers, because nobody wants to listen to scientists. I mean, it's kind of sad, but true. Let me just show you, though, an example. So this group has created this infographic. It's actually at that. You can go to the Solutions Project website, www.thesolutionsproject.org, and you can page down and you can click on a state. So I'll just pick a random state here. And so it gives some of the numbers kind of an infographic form that I showed you, like the percent of total energy demand that could be powered by, under one set of possibilities of wind and rooftop PV, et cetera. And then you can go down, it says the job creation, construction jobs, operation jobs, the power demand reduction due to just converting to wind, water, solar, avoided mortality costs as a percent of GDP, and the actual costs, the footprint area and the spacing area needed to power the state with wind, water, solar, the future costs of energy in the state in 2050, if you adopted one versus the other. And these are the levelized costs of energy. Then this cost savings. There's certainly there's a lot of uncertainty in the numbers. They're not necessarily final. It's still a work in progress, but it kind of gives you another way of looking at it that's a little easier than having to read through thousands of graphs and papers. But anyway, I'm happy to answer any questions if you have them. Thank you very much.
If you have questions, raise your hand and I'll bring a microphone your direction.
Thanks for the talk. I don't think this is working.
Hold it really close to your mouth.
Can you hear me? Okay, I'll just talk it out. Thanks for the talk, Mark. I wanted to ask you about the slide where you showed the wind turbines reducing the wind speeds in hurricanes.
Okay.
Because the typical cutout speed, even for offshore wind turbines, is on the order of about 25 meters a second or 50 miles an hour. And you showed Hurricane Katrina with wind speeds on the outer edge, it was something like 25 meters a second, and then towards the center it was about 60 meters per second. So I'm not sure that turbines would actually be operating in those kinds of conditions, so I was wondering if you could comment on that.
Yeah, definitely. Oops, sorry. So actually the turbines we were using were, for this simulation, well, we use a 5 megawatt and a second set of simulations with a 7.58 megawatt turbine. And their cutout wind speeds were 33 meters per second to 34. Now, so we ran two sets of simulations, one where we actually cut out at those wind speeds, and the second where we actually didn't cut out and allowed it to keep going to the destruction wind speed, which is 50 meters per second, and then cut out. And we found that doing that, because we reduced the wind speeds where the turbines, because the peak wind speeds here, yeah, are greater, but where the turbines are, they're not. They never got up to the destruction wind speed. And it turned out that by using the 34 meters per second cutout, that the wind speed still never got up to the destruction wind speed where the turbines were located, but also the actual extraction of power demand was only maybe 10% less than if you let it go up all the way to 50 meters per second. So, but you could, I mean, the cutout is only because that's what people choose to do. But if you actually design the turbines to cut out at a larger of 50 meters per second, or strengthen the turbine to go up to 60 meters per second, there's no technical reason why you can't go to higher than the cutout wind speed.
Well, certainly there are physical constraints on how large a wind speed you could have and how the turbine still operating, right? I mean,
No, because you just change the gears so that you just maintain a constant power output. That's what they do right now. So the reason they shut them off is they just don't want to damage them. And so by strengthening them, or, I mean, there's no technical reason you can't go up to a higher wind speed than typical, whatever the cutout is.
Are there any new advances in energy storage besides electric vehicles?
Yeah, well, one of the things that's been done a lot now is batteries in homes with solar, for example, so that people can have distributed battery storage. And so it's still pretty costly, but there are a lot of companies now actually doing it. Some of the solar companies are really pushing it and going into that business themselves. And even Tesla creates batteries. They have their own investments in battery storage for homes. So, and also even in power plants. So there's this idea of having people having it in their garages. I mean, one of the people in the group, he has battery storage in his garage, along with his solar system, and works pretty well. So, but it's more expensive than just using the grid electricity, so it's still costly. But there are other ways as well for storage.
Isn't pumped hydro much less expensive than batteries currently? Therefore, anybody that has a large variation in elevation, like mountains in their backyard, can use pump storage.
Yeah, so he's saying that pump storage is more efficient or less costly than batteries, and that's true. So, but pump storage is limited in where you can put it. So, like an individual is not going to be able to put in pump storage unless they have a big property. But it can, on a larger scale, that has been done and can be done. It's not the most efficient use of energy of storage because you're just shifting the times when you're using it. But that's, I guess, what storage does. So that's one of the options is pump storage. So it's it's less expensive if you have the right conditions in the right location. All right, you want to pick people? Okay. Let's go over here.
Well, you have 50 projects, 50 states. Does this assume a national smart grid or a statewide smart grid, or?
Well, yeah, we're treating each state as an island right now. However, in reality, we don't want that to happen. We'd rather have cooperation and interconnection between and among states because that's more efficient, especially small states, like in the south even, where there's not a lot of wind. It's better to have a good interconnected grid where you can get energy when you need it from other states that do have the energy. So the biggest limitation maybe is making sure there's enough transmission over long distances. And again, it's not a technical or even economic limitation, but it's more trying to get people to agree to do it, and the costs have to be distributed in the right way. And you can use a lot of existing pathways for transmission, so you don't necessarily need new transmission lines, but to make the existing transmission pathways more efficient as well. So, maybe over there first.
Yeah, your assumption for, or your results for Colorado showed what looked to be us like a surprisingly large amount of additional new hydro, assuming like 1,300 new hydro plants at 100 megawatts each, I think?
No, well, it was 1.4 new hydro plants of 1,300 megawatts.
Of 1.4 of 1,300 megawatts.
I think so, yeah.
Either way, it's, so in Colorado, we're really sensitive to adding additional hydro plants. And so I'm wondering how much you have dug into or how much you plan to look into the feasibility of really adding, specifically hydro plants at that scale. Because I mean, 10 megawatts is the limit to count for the renewable energy standard in Colorado, and it's a little bit of a random kind of limit, case by case in terms of the environmental impacts.
Yeah, so this is an example where, well, there's nothing fixed about that number. That was just one example. And so ideally, you would have go down to zero. You just have to shift it to something else. Or this is where you're coming from out of state. You might take out of state hydro from a nearby state that actually has an abundance of it. And so, yeah, I'm not trying to prescribe that. That's just one option if it takes, and you could get some of that from just increasing the efficiency of existing hydro as well. And some of that could be just run-of-the-river hydro that doesn't have to be large, it doesn't have to even involve dams. It could be run-of-the-river in some cases. Over here.
When utilities do these analyses, they're constrained by a couple things. One, they have all their investments existing in fossil infrastructure, including the coal plants. So first I'm asking whether you consider stranded costs. The other thing they do is they discount their future fuel costs at their weighted average cost of capital, even though we pay the fuel. When you discount heavily, you make those future fuel costs look small. So I'm wondering what discount rate you might have used as you looked out.
Well, okay, so our plan is such that all new energy would be clean by 2020. So that means that when you have a new power plant proposal, instead of putting up a gas plant, you put up something that's clean. Or every new car that's bought is a battery electric car, for example. And so that way, you don't get stranded assets because you gradually replace the existing infrastructure due to natural retirements. Now, you would have some policies in place to push the dirtiest ones out faster. So there you get some stranded assets, but the cost to society of those assets is so great because of their air pollution damage that there's actually not a loss just to the companies, but they didn't care about your health, so why should they care about that?
And the discount rate, what discount rate do you use as you kind of value these, as you think about costs?
Well, I don't remember the exact numbers offhand, so I'd have to look up the discount rate. Yeah, go ahead.
Hello. Your analysis seems to rely very heavily on the idea of utility scale systems, solar, wind. Did you or do you have plans to try modeling alternative like distributed energy resources, particularly small-scale hydro, small-scale wind, and small-scale solar as an alternative to this utility-scale development?
Oh, yeah, yeah, so on all our solar, all our maps have PV rooftop solar and for commercial government buildings and residential, so that's distributed solar.
Yeah, but you're understating, you may be understating that. You referred to Germany, and Germany has had a much different scenario there with rooftop solar. So there, you know, for instance, you rank number 2, concentrating solar power. However, that there's some severe institutional issues, barriers and issues around that type of large-scale development. What about tipping it the other way and modeling the whole system from the bottom up?
Well, that ranking was a little bit different than what's actually implemented. The ranking is based on what would give you the least impact. The reason CSP is a little bit higher ranked than PV is because the embodied energy in producing a PV cell is greater. So you have more carbon emissions if you use the current grid to create that PV. Now, if we go to 100% renewable energy, then it doesn't matter what's used to produce the PV, and then the rankings would be more equal. So that was just based, but that doesn't mean we would favor, that list just tells you these are the ones we want to choose from. It doesn't mean we just use more PV more CSP than PV. But, you know, Germany, I mean, the numbers we have, we saturate the rooftops here. I mean, most of the rooftops are covered. You just need so much energy. So there's a lot of distributed energy. Now, and also even with hydro, the hydro does not have to be large-scale hydro. It could be, as I said, run-of-the-river hydro, small-scale hydro. Wind, you know, you can also include backyard wind, but it's less efficient. So we're not one way or the other saying you should use it or not. That could be, these are the number of wind plants are just, that's how many, if they were 5 megawatts, but you could have a bunch of smaller ones but more smaller ones, but you'll get less energy per dollar spent because the cost of small-scale wind is.
So model that next time.
Well, okay, thank you. Yeah, go ahead.
So I share your enthusiasm for going 100% renewable electricity generation, but when it comes to transportation, I'm a lot more pessimistic. Like, you know, electric vehicles are still expensive and they're going to for the future. Lithium is like a limited resource. It's largely, I guess, concentrated in Bolivia. And when it comes to fuel cells, they're like not even commercially viable. So I was just wondering your reasoning for using it.
Well, so there's enough lithium in known locations to provide lithium for 3 billion vehicles, and there are about 700 million vehicles in the world. So, and they keep finding new lithium resources every year. So I'm not worried about the lithium being short. And now for fuel cells, yeah, it's not commercially viable. There are some fuel cell vehicles being sold in Europe right now, and so it's becoming more commercially viable. But you would want to electrify as much as possible because electricity is more efficient than hydrogen fuel cells for transportation, but hydrogen is still more efficient than internal combustion. So it's actually 3 times, you get the cost of, you know, electric vehicle per mile driven would be 1/3 that of a hydrogen fuel cell vehicle. But the hydrogen fuel cell vehicle would still be about 2/3 to 3/4 that of gasoline. So it's still a benefit to try to go to hydrogen if it's economically viable. I forgot your last question.
Yeah, I was wondering about, at least for the United States, typically the scenario that you proposed has a lot of onshore wind in the Midwest of the United States. And I was wondering about climatologically the danger of severe storms and tornadoes. I mean, you mentioned hurricanes here, but if there's a maintenance cost that your study takes into account, or is that part of the study or not?
Well, I mean, if you actually look at what's on the ground, happening on the ground, I mean, you know, Iowa and South Dakota, they produced 28% of all their electricity last year in 2013 from wind. And their grid didn't go down, and their turbines weren't destroyed. So there's an interesting question. If you have a lot more turbines, even maybe you decrease the chance of severe storminess, like tornadoes. Interesting research question that you were talking about earlier. So there's this huge growth already in Texas. I mean, so they don't seem to be so concerned about it. Sure, if a tornado hit the path, then probably would or could destroy some turbines, but maybe not that many. If you, from an insurance point of view, it might be a small risk, because the path is so narrow that the chance of it actually hitting is really small. Okay.
So what actions can we take to make this happen faster?
So this comes down to the levels. At the personal level, people can do things, and at the policy level, so people can instigate the policymakers to do. So at the personal level, certainly understanding where your energy comes from, and if you're interested, when you invest in new appliances in your home, want energy efficiency energy efficient appliances, putting solar on your roof. If you have wind in your backyard, you might put in a small scale backyard wind turbine. The next vehicle you buy, an electric vehicle. I mean, think the Tesla Model S. I mean, even though it's still expensive, I mean, relative to, it's not so expensive relative to an SUV, but it's $60,000 to $100,000. But it is the safest car in the world in terms of driving. It's goes 310 miles on a charge. It can be charged now in 1 hour. It's got an acceleration that's incredible. It's a beautiful car. I mean, these are the technology is changing so rapidly. Getting an electric car would be something that a lot of people would want to do. But also, just your electricity, as I said, solarizing using energy efficient light bulbs, LED light bulbs. But then just pushing your policymakers to do the same thing and to try to change the local community energy mix so that it's cleaner.
I will ask the last question. Mark, you said that there are a lot of students here, and I'm wondering if you have any recommendations for what skills they should be trying to gain while they're in college in order to help move our economy in this direction.
Well, if you're studying this issue, there's a science part of it, and there's the policy part of it too. So those are interested in science, certainly working towards developing either new technology or improving existing technologies, studying, a lot of our students are studying, what are kind of systems approach, like looking at grid integration of renewable energy is a big field. When you put in a lot of renewables onto the grid, how can you maintain that grid, keep it stable? So some of that's power electronics, some of that is just optimization, mathematics. So there's a lot in this overall systems. There's a lot in technology development, and then there's kind of bringing the information to policymakers. So there's a lot of public outreach, and so there are a lot of areas in education at universities in particular where people can focus on and actually help this along quite a bit.
So let's give Mark a round of applause.